I thought this was going to start at 3. It says 3 on the thing. It says 1:30 on the door. So I was busy completely chilling out. So just give me a second to like regain my composure. Okay. Also, March meeting was last week, so I'm still a little hungover. Okay, so down to business. So I was originally going to give a talk that was going to be about some gravitational work that we were doing, but then I realized that this probably wasn't the best forum for it. But now that we've gotten to Friday, I realized that it was probably the perfect forum for it, because another talk on topological superconductivity is probably not going to be very thrilling. Using that as motivation, I'd like to talk about the people who are either to be acknowledged for this work or to blame for this work, depending on how you think about it. So this was another part where it was kind of a little bit disappointing for me, because normally I would think that it was a good idea to show a picture of my group. But then I realized that this was a series of people who were not going to give up this career in science for a career in male modeling, so I decided to just list their names rather than have a picture of any of them. So these are the students whose work I'm going to be presenting today. As is normally the case with faculty members, I didn't do anything except say, yes, this looks right. And this has also been through collaborations that we've had over the years with some of the experimental people, both at UIUC and at Princeton University. As is always the case, there's a lot of really interesting and nice work, so if I didn't cite your papers or the ones that you think are particularly great, sorry. Send all of your angry comments to this young man. It's for no other reason than he's a sweet kid and he wouldn't really know what to do with it, and not because I'm sick, I would find that amusing. All right. So, the outline for today's talk. So it's a completely imbalanced outline. So what I'm going to do is sort of give you the introduction to the problem that I thought was particularly interesting about looking for proximity-induced topological superconductivity in three-dimensional topological insulators. And then once I give you the introduction, hopefully you'll be interested in the rest of the talk, which will be mostly about some of the different ways that we've been trying to understand some of the experiments that have been coming out, and give some sort of roadmap as to where we can look to a little bit more efficiently to find non-conventional superconductivity. And then there is, if I have time, depending on how many funny jokes I can come up with on the fly, there's also this other section about unconventional superconductivity that's beyond sort of the normal proximity-induced superconductivity, and then hopefully I'll draw some interesting conclusions. I didn't even notice that you guys were coming in. All right. So this is the standard introductory slide for why these systems are interesting. Don't worry, I do the same thing when students come in late. I just sit there and stare at them. You can think of it in a number of different ways. So this is, you can think of your own jokes for this particular slide between red halves and blue halves. It used to be Republicans and Democrats, but that was prior to 2016. So now that you could say that this is maybe one side would be Trump and the other side is reality. And then in the middle there's something happening, but we're not quite sure what it is yet. By using these things as different combinations, so I can take the red half. Don't leave. So we can take the red half and the blue half, and we can code it with different things. So I can code it with either magnetism, so with magnet pointing out of the plane, magnet pointing into the plane. Of course, then at the interface, I should have some quantum Hall state. If I were to code it with superconductivity, where I have a positive gap, a positive order parameter, a negative order parameter, then at the interface, I would expect to see a chiral fermionic state. I'm going to try and avoid this guy. And if we code one with magnetism, one with superconductivity, then we expect to see a chiral state. So using this as sort of motivation, this is the system that we were really interested in studying, a superconductor on the top of a topological insulator, and this follows in the seminal work that Liang Fu and Charlie Kane had done in predicting that there would be unconventional superconductivity based on this proximity coupling within the system. So the trick was that apparently it's a much more complicated structure to make than it is theoretically to study. I can draw these little structures all day long, but apparently that doesn't really give anybody an idea of what actually happens in these systems. So this is sort of the odd slide in that I'm going to try and explain to you what they do to make these things. Basically they start off with niobium selenide, which is a superconductor. It's actually a more interesting superconductor than we originally had thought. In the later parts of the work, we actually started taking into account the real band structure of this superconductor to try and give a more realistic picture of the kind of pairing that was going on and exactly where we could find interesting states. And so on top of this, they grow a bismuth layer because what they're interested in doing is making sure that the strain is not too terribly difficult. And then they start growing quintuple layers of topological insulator via molecular beam epitaxy. Based on proposals that I've reviewed over the years, you can use MBE for a bunch of different things. Depending on their productivity, it could be make-believe experiments, or also, depending on their budgets, it's mega-bucks evaporators. But sometimes they're successful, and when they are, then you can see that for 6 quintuple layer systems at 4.2 Kelvin, you can see that they start developing in a superconducting gap in these thin films of bismuth selenide. And this is just because, of course, because as you cool down, then niobium selenide becomes superconducting. And eventually what you can do is you can see this is evidence of superconductivity because you apply a perpendicular magnetic field to kill off the superconductivity. And so as you increase the magnetic field here for a 3 quintuple layer system, you see that the gap starts to close. Okay, so this is good things. So here we see 2 different samples, and so this is for a 3 quintuple layer system, and so the gap that we see here is the hybridization gap. And for 6 quintuple layer system, of course, it's sufficient enough where the penetration of the surface states into the topological insulator are sufficiently decayed where we don't have any hybridization gap, and since time reversal symmetry is still obeyed in this system, even though we've coupled it with a superconductor, we still expect to see the Dirac point. And the interesting thing about this system is in the quintuple layer system, we also see Rashba splitting. So this Rashba splitting comes from the fact that when we grew when somebody else grew the bismuth layer, there's a charge transfer in between the bismuth and the topological insulator. And so what this does is it creates an electric field, and the electric field increases the Rashba splitting. And so you get this interesting effect here. So other things in the 6 quintuple layer system, obviously, as I mentioned, there's no hybridization gap. And the big question was, okay, if you can grow these systems now, what would we expect to see? And so this is where we started doing our theory. So we started by doing a kind of non-trivial calculation. It's certainly more trivial than some of the calculations that have been presented here this week. So I'm not going to say that it's a very complicated one. Hard for us, maybe. We're just a simple group of engineers. So this is the system that we were interested in studying. So what we tried to do is we wrote down all of the in-plane components in momentum space, and we kept the out-of-plane components in real space. We wrote down the Hamiltonian, typical 4-band Hamiltonian with 2 spins and 2 orbitals. And from that, then we were able to write down the Hamiltonian both for the superconductor, so the in-plane part for the superconductor, and the topological insulator part. So for the first 10 layers of the 14 layers that we studied are all going to be superconductor, and then the last 4 were topological insulator. The reason that we chose 4 quintuple layers for this particular structure is because of the fact that this was the system that we had primarily results for that were experimental, and so we thought it would be a much more interesting paper if we actually sort of tried to simulate the exact same system. So the out-of-plane components, again, we have the metal components here, which is nothing interesting, and the out-of-plane components for the topological insulator. Then, of course, we add the mean field density-density interactions, and so this, I'll speak a little bit more about the size of the U that we chose. The A orbitals, so the A orbitals represent the pz orbitals of the bismuth atoms, and the B orbitals represent the pz orbitals of the selenium atoms. And what we can do is we can say, okay, in the continuum limit we have a series of symmetries associated with this, so it'd be a good idea if we sort of keep these in mind as we start formulating the solution. So we have, of course, time reversal, C3, so this should be 3C3V, but when you combine it with the mirror symmetry, this is my C3V. And we have, so fine, it's time to choose a mass. And so it's topologically non-trivial for this parameter range. And for our particular system, we had a lot of access to exactly how large the gap was from ARPES data. So we were able to sort of play around with the mass term until we got a hybridization gap, which was exactly the same as the hybridization gap that was found in the experiments. Okay, so now what we have to do is, obviously it's a superconducting system, so we have to expand it into PDG. There's nothing tremendously difficult about this part, but to be as realistic as possible, we wanted to choose something that was going to give us an experimentally verified gap in the superconducting region. So we choose a U that was 1.2 electron volts. And furthermore, we set so in order to get at least when we started these experiments, it was very difficult to get the chemical potential of the topological insulator into the sexy regime. It was always up in the bulk bands. So to be consistent with that, for the topological insulator, we set the chemical potential up into the bulk bands. And because of the fact that it's a topological insulator and it's not a superconductor inherently, then we set the pairing inside of the topological insulator to be 0. So one of the things that you're probably asking yourself is, that seems a bit ridiculous, because at the end of the day, what you're going to want to ask is what kind of superconducting pairing develops in the topological insulator. So if you set the pairing to 0, then it's going to be very difficult to do that. But it turns out that if you take the expectation value of the creation operators, gives you all the same information. You'll be off by some constants, but it's not going to give you, it's going to give you the same sort of functional form. So in the end of the day, we're still going to be okay. So then once we've created this entire recipe, then we iterate over this self-consistently calculating the density interaction, the densities, and we do this until we get discrepancies which are on the order of about a microelectron volt or so. And then after that, we calculated and we said, okay, we tried all the different combinations, and we tried all the different combinations because of the fact that the student that I had that was doing this didn't look at the symmetries. So that meant that there was a large panel of data that I had to look at rather than this very small, meaningful panel of data. So what this is simply I have a singlet component, which I would expect because I have proximity coupling from S-wave superconductivity. And then I have 2 triplet components, and I expect these because of the fact that I haven't broken time reversal symmetry. So I would expect there to be I would expect there not to be one over the other. I would expect there to be both of these. So we can think about these in another way in terms of symmetries, which would have made this a lot easier. So the singlet is, of course, it's an intra-orbital pairing. We can have singlet and triplets pairing occurring in the same system because of the fact that we have broken SU2. So this is my typical singlet component, and then beyond that, I have my triplet component. So I have my even parity triplet component, and I have my odd parity triplet component. And of course, both of these triplet components can exist because of the fact that at both of the topological insulator surfaces, I have broken inversion symmetry. So once I do this, why is this happening? Okay, I just explained why that's happening. See, this is what happens if I had that extra 30 minutes or hour and a half. I could have remembered that I wrote that out. So the question is, okay, what kind of superconducting pairing is there? So when we calculated this, we found that, of course, you have the S wave and you have the P wave, and when you add that all together, then you get something that we called helical pairing. And we can also look at the in-plane components of the superconducting order parameter, and we can see at the edges, of course, we have the S wave. So this is my S wave components. This is my S wave surface state, and then I have the S wave bulk states, and then beyond that, I also have my P wave states, and of course, These are doubly degenerate bulk states, so I'd expect there to be singlet pairing there. The surface states are not doubly degenerate, so this is why we see the P wave accumulating in the surface states, but not in the bulk states. So then at the end of the day, it's a combination of Px, it's S plus or minus S plus Px plus minus IPy. But this was a nice program that we'd written, so we could ask about decay of the superconductivity into the topological insulator. And so this are the experimental results for several measurements that they did on different bismuth selenide quintuple layer thicknesses. And we see that we get basically the same sort of functional form as the experiments do. And so you can sort of see, okay, well, we can back out from the experimental data and try and understand what's going on. And so for this, we saw that the coherence length, the mean free path was for these bismuth selenide samples was about 16 nanometers. And so when you calculate the coherence length, it's about 23 nanometers. And so that explains more or less what we see in the bulk, but it doesn't necessarily explain what's going on in the surface. But to think about what's going on in the surface states and why they're decaying a little bit faster than the bulk states, you can think about it in terms of maybe a density of states argument, where I'm taking the surface states and I'm forcing them farther and farther apart. So it's a little bit more difficult to sustain superconductivity within the surface states as I continue to increase the film thickness. Depending on who you talk to, if you talk to Zahid, I think that he claims that you can see proximity coupling up to 9 quintuple layers, but from at 9 quintuple layers, from my perspective, that kind of looked like 0. So I called it 5. 5 seemed like it was an appreciable value. After that, it seemed like the bulk started dominating. So we can also say what happens when we start playing with chemical potential. So this is when the chemical potential is sitting inside of the bulk gap. So this is where we're in the topological regime, and for 2 unit cells, so 2 quintuple layers, you can see that we have sufficient number of states where we can actually have superconducting pairing. And so you see the surface states here. As we start separating it out, the surface states decay into the bulk, and I don't have enough to be able to stabilize superconductivity, and so the superconductivity decays relatively quickly. If I were to do the same thing but take the chemical potential and raise it up into the bulk, then I would expect to see the superconductivity persist a little bit differently, which is what we saw experimentally when we were looking at the decay of the order parameter into the bulk of the topological insulator. So this is the case, of course. So when I look at this, is again my singlet pairing. So I have my bulk states, I have my surface states, and in this case, you can see that it persists. The superconductivity persists in both the bulk and surface states as I continue to separate the two, because I have the presence of these bulk states to be able to stabilize my superconductivity. So, fine. So this is where the question really came in, for me anyway, is what do you actually measure? You can determine that indeed superconductivity is coupled into the system. So these are the measurements from the Princeton group, where you can see the momentum resolve gap at different points that they slice through the Fermi surface. And this is probably where the paper went from being one that went to science to one that went to nature physics. And this is because of the fact that when you looked around the Fermi surface, said, okay, what's the gap? It looks isotropic. And of course, it looks isotropic because you have a persistence of S waves, of S states. S states are, of course, isotropic. They're trivial under all rotations. They obey all the symmetries because we're just having them coupled in from a traditional S-wave superconductor. Another thing I might want to mention with these simulations is that we haven't taken into account any of the realistic parameters within the superconductor to actually have like a realistic surface picture of how the Cooper pairs are tunneling in. We're simply using a tunneling matrix to get the Cooper pairs in, and so we can sort of vary that, but it's not as accurate a model as you would perhaps like. So this was a little bit irritating to some people more than others, but it's an understandable result. So then the question is, okay, it seems like theoretically speaking there should be some way of seeing this topological superconductivity. Experimentally, it's a quite different problem, so what can we do? So looking for topological superconductivity. So here's the problem, and this is, of course, why there's the problem. But what can we do about it? So we have a bunch of parameters that we can manipulate, including magnetic doping and the chemical potential, just to name a few. So we can do this. It's a little bit, these are much easier, like, not all that much easier than, this is much easier than adding additional magnetic doping, but it's still a little bit easier, I think, than growing additional quintuple layers. So we didn't really play around with the quintuple layers quite so much. And so we're going to approach this in two ways. So one, I really wanted to come up with a simple, intuitive picture of when I start adding in things like magnetism, how do I expect these things to change? We could simply plug magnetism back into the program that we'd already written to understand the topological surface states, but that's not necessarily going to give us a very good picture of what's going on. So we need to have some simple analytical picture before we move to a more detailed numerical model to understand what's happening when we start adding things like magnetism. So the idea was, if we were to take this system, add magnetism, then naively what I would expect is that the bulk states should decay relatively quickly. They're just singlet paired, so if I add magnetism, then I'm simply breaking them apart. But where if I have the topological surface states, then the S wave might decay, but then the P wave would persist because I'd either have up or down, and so then this would break the degeneracy, it'd break time reversal symmetry, and voila, chiral state should appear and everything should be just fine. So they had some unpublished data that was on magnesium doping inside of topological insulators that were grown on top of this niobium selenide base. And you can see that the superconductivity decays relatively quickly as a function of manganese concentration, and more specifically, if you look at the 4%, you can still see that there are some signs of superconductivity within the slices of in momentum space of the binding energy and the intensity of the signals that they receive. But when you get to 10% manganese concentration, then of course nothing interesting is happening. So the question for us is, can we really use magnetic impurities in order to be able to get the type of topological superconductivity that we're looking for? That shouldn't be there yet. Again, it's because we had an extra hour. So what we did is we started with a very simple model where we just take and form a topological insulator Hamiltonian. So this is based on the work of Marcel Franz. And his name is not on this slide, but it certainly deserves to be because this is where we started. He came up with a very nice model that's very simplistic. It takes away the bulk, and for doing an analytic calculation, getting rid of the bulk is really a really handy thing to do. So we have the top and bottom surface states connected by some sort of simple term. Now, what we're doing is we're adding in magnetism, and so we're assuming that the magnetism is pointing perpendicular to plane. Obviously, when you add real magnetic dopants in, and this is why I think there are some discrepancies with some of the recent experiments, when you add real magnetic dopants in, obviously then they're going to not all be aligned with the surface, but we're assuming that there's some on-aggregate field that's pointing out of the plane of the topological insulator. So when we put this together, so we had to do some tricks so that you can, sure enough, use this Hamiltonian, add in the Zeeman terms, and you can get a very messy-looking Hamiltonian. But if you want to be a little bit more elegant, then what you can do is you can start doing some rotations. So you can perform an SU2 rotation on both the spin sector and the layer sector, so that in the real spin and the pseudo spin. And what you can do is you can come up with a very simple, get a hybridized basis as soon as you start making these rotations. But what you get is a simpler Hamiltonian. So then what we did is we add the superconductivity in, and we get a Hamiltonian that looks like this, which is much easier. So this is the hybridized basis that I was interested in looking at. And so one of the things that you can see is basically we have two different sectors here. And I'll show it a little bit more clearly. So you can think of this as maybe sector 1, and these off-diagonal terms here as a different sector here. And so this is how we're going to proceed with this problem. So this would be sector 1, where I have some hybridization gap, and so I'm basically looking at these states here, and then I can think of these other states as a separate sector separated by magnetization. Now, if this magnetization goes to 0, then all of these states fall onto the same line. But there's going to be one that's going to be pushed up, one that's going to be pushed down by the addition of this Zeeman term. Okay. So let's take our BDG Hamiltonian. So this is after we've added superconductivity. Topological surface states for top surface, bottom surface, and we have the BCS coupling. And so now what we do is let's look at the top layer. So this is, we can sort of break this down. And so then again, this is taking this form of this matrix that I'm showing here is after I've taken the pairing matrix, and I've also performed the same SU2 rotations on this pairing matrix. And so what I can do then is I can say, fine, I want to take this and have a symmetric combination. So when I think of symmetric combination, what I'm thinking about is pairing between different sectors. So in this sector here, the same sector, plus k and minus k in the same sector. However, if I were to think about these off-diagonal terms here, this is sector 2 as I defined it, and so this is intersector pairing. So this would be if I had an electron that was in one of these other sectors, and after I split this with the Zeeman term, I still want to pair it with an oppositely an electron in the other sector with an opposite momentum, opposite spin, opposite momentum. But you can already see one of these is going to be dominant and the other one is not going to be dominant, because you can think about this is going to be costing a lot more energy when I start increasing the form of the Zeeman term. So we wanted to be sure that this is what we were doing, so what we wanted to do is calculate, so we can separate these out into two separate things. We can have a symmetric sector and an antisymmetric sector, just like we'd written before. And because of the fact that the order parameter decays within the system, we can split these up and look at them individually. Otherwise, we couldn't do that. So naturally, what we do then is we look at the top and bottom surface correlation functions for the superconductivity, and we've plugged in all of the parameters that we have for the experimental system that we took from both of these papers. And you can see that as we increase the Zeeman splitting for these two different sectors, then the antisymmetric sector, so this is pairing between electrons that are within the same sector, is going to be dominant over the symmetric pairing. So, okay, changes the form of the pairing. Yeah. Now, so now that we have this simple picture, what we can do is we can calculate a phase diagram. And we can do this basically by looking at the band closing points within the topological insulator as a function of the magnetization, as a function of the chemical potential, and as a function of the hybridization gap. So everything is just basically normalized by the hybridization gap. So when we do that, we can analytically calculate exactly what the phase diagram looks like. So our phase diagram looks pretty much like Socheng Zhang's phase diagram that he calculated for a system very similar to this one about a year before we finished this one. There are some subtle differences which we can talk about later, but more or less we came to the same conclusion. Obviously what we can see here nicely is that, so what I've done is I've tried to plot out the different sector 1 and sector 2 contributions and all of the different crossings, assuming that this white line here is the chemical potential. And so as we move the chemical potential up, we can see that we can go from different Chern numbers, and as we increase the Zeeman splitting, we also get different Chern numbers that change as we close the gap. But crossings that occur up in these bands here, where we move one band across the other band, are not going to change the Chern number because of the fact that you haven't actually closed the gap anywhere. So, okay, good enough. So, what I want to do now is I want to think about, actually I don't want to think about this because I only have 5 minutes. Let's get to the punchline of this particular slide. I thought I had 40 minutes. It's so clear there should be no questions. It takes care of that. Okay, I'm going to slow back down then. So, So we have the top and bottom surfaces. So what I wanted to do here is I wanted to say, okay, let's see if we can, using the simple analytic model, we can see that, and sure enough, this is looking just simply at the S-wave component. As we increase the S-wave component, then what happens is you get this pairing in between these two. So these are the difference. This is top and bottom, and sure enough, we can see that the S-wave order parameter for the top surface changes. And this is because as we transition through this Zeeman term, then we go from a symmetric combination to an antisymmetric combination. So maybe one thing that's kind of interesting is you think, okay, if you have an antisymmetric combination where I have a different order top surface and a different sign on the bottom surface, then I should be able to measure some sort of interesting Josephson effect in between the top and bottom surfaces. So there is one paper on there, I think a PRL from a couple of years ago. But anytime we sort of asked an experimentalist to try that, they made a funny face and just sort of walked away. I assumed that was to go do measurements, but so I think maybe I was wrong. All right. So one of the things that I thought was really particularly interesting, so when we moved away from this analytic model and started calculating really what was going on within the system, as we started adding in disorders, this is an interesting result that came out, and this is what happens when we look at coupling between the topological insulator and the superconductor. And we never really thought too much about how the bands changed, but if you consider strong coupling, that what you can see is when you compare this to weak coupling, so what you can see is that the bands for the topological insulator are relatively significantly changed by the fact that we now have much stronger coupling between the topological insulator and the superconductor. Whereas in this case, you have so the hybridization gap changes, and the hybridization gap changes within the strong coupling region because you have some structural inversion asymmetry that causes surface charge accumulation. But in the weak coupling regime, which is mostly what we're dealing with here, the band structure of the topological insulator is relatively unaffected. But I thought that this was a particularly interesting result, and so around the same time, we thought, there were a couple of papers that were talking about this concept of an inverse proximity effect, where instead of doing measurements within a topological insulator, what it might be easier to do is do measurements within a superconductor, because superconductors are going to be a lot more easy to sort of understand some of this phenomena. So if you can couple in the topology, then you can actually make measurements within the superconductor and hopefully see something a little bit more clear. And so I wanted to see exactly how much inverse proximity you could get by using this sort of trick of varying the coupling. And it turns out that in order to be able to get the topology, so in this case, since it's time reversal invariance, then we have spin orbit coupling that actually starts bleeding into the superconductor. And so you can see this is the superconductor, and this is the P wave, and you can see that for very strong coupling, then you can see clear signatures of the topology within the superconductor, whereas within the weak coupling regime, then you see almost nothing. So this is superconductor up here, and so this is TI here, and this is superconductor. So you can see there's some signal here, but there's no signal here. So we wanted to visualize sort of the relevant physics, and so we can sort of confirm that we actually have a switching from symmetric to antisymmetric by looking at different points. So this is, of course, the superconducting order parameters. So this is both S and P. We have the chemical potential here is in the bands, is not in the bands, sorry, it's in the surface states. So this is why we only see the surface state contribution here. But as we continue to look farther and farther within the topological insulator, as we go from the bottom to the top, so this is where the superconductor is directly connected. This is the top where you actually make measurements, and you can see that it switches sign. So good. So one of the things that I want to do now is think about not necessarily the S, but the fate of the P wave. And so what you can see here, so what I've done is I've calculated as a function of exactly what's happening with the both S in-plane components and out-of-plane components. And the thing that's nice about this is it sort of clearly illustrates the issue of why it's going to be very difficult, or why I thought it was going to be very difficult to find topological superconductivity in these systems, because when you actually start adding in the Zeeman term, you don't just separate spin states. You can separate that in the bulk, that's no problem. But what happens in the surface states is you start canting spins. And so even though you get as soon as you turn on a Zeeman field, you get an out-of-plane component that gives you an imbalance between the px plus py and the px minus py. you actually still have some non-zero projection of the S-wave component within the plane of the topological insulator that still gives you some helical pairing. And as soon as you still have some helical pairing, you're always going to have some S-wave contribution here, which was kind of a bummer. So we can sort of correlate this very nicely by projecting the full wave functions that we calculate from our complicated numerical calculations onto the surface, and so you can sort of that we can in fact correlate nicely this out-of-plane canting with the amount of P wave that we should measure. That looks horrible, but the thing is that so this is a really neat and interesting experiment, and I think this is probably where I end. Okay. But this is an experiment by the UCLA group, which is filtering its way through science, I think, where they actually took a thin film topological insulator and they doped it with chromium. And so what they did is they were able to create a quantum anomalous Hall state. So they have a quantum anomalous Hall state that's running around the outside of the topological insulator. They put an S-wave superconductor on top of it, and they see these these plateaus at certain magnetic fields at half E squared over H. And so this is an interesting experiment, certainly indicative of some theoretical predictions by Soch and Zhang's group, but it's not exactly quantized to half E squared over H. And just like Duncan Haldane said, if it's topological, then it shouldn't be half plus or minus 0.02. It should be half. So what I think is happening in this case is as soon as they're flowing a surface current, then there's a non-zero torque turn that opens within the system, the spatially varying Zeeman term, and this is what's causing it to be not completely quantized. So if you're interested in the second part of my talk and additional jokes, I'm here all week. The price is alcohol. But thank you very much for your patience and attention, and I'll happy to take questions.
Thank you very much. Even though everything was clear, we have time for a few questions.
If not, I can fill this with